Hi and welcome to this tutorial on bond polarity. In the previous tutorial, we had a look at different types of electron pairs, so lone pairs and bonding pairs, and we used that information to help us predict the shapes of molecules. So in this tutorial, we're having a look at electronegativity, polar and non-polar bonds, and polar and non-polar molecules. I've got an image here of a molecule of water with its electronegativity values included. So the atom of oxygen has got a certain electronegativity and the atoms of hydrogen have got their own set electronegativity. So what do I mean by electronegativity? It is the power of an atom to attract the bonding pair of electrons in a covalent bond. So oxygen here has got a higher number, so 3.44, and it's therefore able to more strongly attract that bonding pair of electrons in this covalent bond here. So if I represent those here, so one electron from the hydrogen, one electron from the oxygen, they are going to be held more closely to that oxygen atom. If I draw another image up here to make that a little bit clearer. So if I've got a pair of electrons being shared, they're going to be held more closely to the oxygen atom than they are towards the hydrogen atom, because oxygen is able to more powerfully attract that bonding pair of electrons because it is more electronegative than hydrogen. When we've got a molecule where both the atoms are the same, there is obviously no difference in electronegativity. So that bonding pair of electrons are held perfectly in the center. Okay, now there's obviously an attraction between the positive nucleus and the negative electron pair, but in terms of a tug of war, we've got exactly the same person on both sides of the rope pulling the same amount. So these electrons are held right in the middle, equal electronegativity. Okay, so an element is more electronegative if it's got a higher value on what we call the Pauling scale, and those are the numbers that I was showing on the previous slide. So if an element is more electronegative than the other element that it's bonded to, then the atom will attract the pair of electrons towards the covalent bond itself. But in this particular case, we've got a situation where both of them have the same number on the Pauling scale because they are the same atom type, so it's held perfectly in the center. So the Pauling scale, we've got a lovely example on this periodic table here. It measures the electronegativity of each element, and each of the values are shown below the element symbol above. So you can see that fluorine is the most electronegative element, 3.98. It's got the highest value. And if we go down here, we've got some very much lower values. And you can also see a general trend as we go into the top right-hand corner in terms of the electronegativity, also shown by the colour hue from yellow to red. As I said before, when we had Cl2, both of those atoms are the same. So we had equal electronegativities, so the electrons were attracted equally. So they were bang smack in the middle of that bond. I've got my image down here showing that going on. When we come across two atoms that are covalently bonded that have different electronegativities, such as carbon fluoride, we've got something called a permanent dipole. So fluorine is a lot more electronegative than carbon. Therefore, that pair of electrons in that covalent bond is held much more closely towards the fluorine than it is towards the carbon. So the way we represent that is we use a Greek symbol called delta. And there is our delta up here. So it becomes delta negative. It's a partial negative charge. These electrons are negative. So when they're held more closely towards the fluorine, it makes the fluorine feel a little bit more negative. So it gets a delta negative charge. And our carbon is obviously left electron deficient because one of its electrons, imagine this is one of the carbon's outer electrons that it's formed a bonding pair with, it's been pulled away from the carbon. So the carbon's now feeling electron deficient, so we give it a delta positive charge. So electronegativity is obviously different for each atom, and the difference between the two values that we find in the Pauling scale tell you how stark that difference in polarity is. But as I said, electrons are pulled more towards one atom than the other when we've got two different atoms bonded together. So like I said, we've got it being pulled more towards the fluorine. I'm showing it very extreme on this image here, but I could show it slightly less extreme. So it's just more towards the fluorine than the carbon. And there's my delta negative and there's my delta positive. And yeah, like I said, this is a permanent dipole. It is there all the time. as you saw, the charges that represent the dipoles are known as, we've got delta positive and we've got delta negative, and these are also called like partial positive, partial negative, but you need to be able to draw these symbols very well. Sometimes I don't always draw them particularly clearly, but they mustn't look like an 8 or an S. There must be no ambiguity, so make sure you practice drawing that symbol. Let's have a look at an example of hydrogen fluoride. So in HF, there's a single electron pair between the H and the F, and that's represented here. And so we've got a covalent bond. But the fluorine's got a much higher electronegativity than the hydrogen. So there's a stronger pull on that pair of electrons. So the electron pair is closer to the fluorine than it is to the hydrogen. So we end up with a delta negative on my fluorine, leaving my hydrogen with a delta positive charge. It's electron deficient as such. So these permanent dipoles that we show lead to what we call polar bonds. Okay, so the bonding between hydrogen and fluorine is called a polar bond because these two atoms have different electronegativities and the electrons are asymmetrically distributed. So unlike chlorine, where we had Cl with the electrons right in the middle, in HF, they are asymmetrically distributed. They're closer to the fluorine than they are to the hydrogen. And therefore we get what we call a permanent dipole. So that delta negative and that delta positive on those atoms. And the higher the difference, the greater the difference in the electronegativity, and you can work that out from the Pauling scale, the greater the difference in the numbers in the Pauling scale between the two atoms, and the more polar the bond is. And in summary, polar bonds form between atoms of elements with different electronegativities. That's the main thing we want to get from here. We get non-polar bonds from atoms that are bonded to the same type of atom. So if we've got chlorine and chlorine, then it's a non-polar covalent bond. The electrons are going to held perfectly in the middle. Think of it as a tug of war. We've got two of the same person pulling both sides. They're not going to go more to one side than the other. They're going to be held perfectly in the center. Or we can also call something non-polar when the two atoms have got very, very slightly different electronegativities. It's negligible difference. So CH, carbon and hydrogen, have got relatively similar electronegativities in terms of the Pauling scale. So we also refer to a CH bond as non-polar. That's important to remember. So the electrons are symmetrically distributed between the two atoms. Okay, so it's what we also call a pure covalent bond. You might hear it referred to as that. So sometimes the polarity gets so extreme between the two atoms that we get the complete transfer of electrons. And that is ionic bonding. So when you actually look at the periodic table, when you learn, even at A-level really, we don't go into this in too much depth, but we talk about groups 1 and 2's ionic bonding, and then we talk about covalent bonding, ionic bonding with groups 6 and 7, for example, and then we can talk about covalent with non-metals. But there's actually an array. And aluminium, for example, in group 3 has got different properties, and we can get different degrees of covalent ionic bonding. If we push the polarity to the point where the electrons are so far towards one atom, there is a big difference in electronegativities, that is where we get that complete transfer. So yes, with sodium and chlorine, we've ended up with the electrons being completely transferred to the chlorine, and that creates a full charge instead of a partial charge. We get a formal, full negative charge rather than a delta negative. Okay, so in terms of the strength, we can talk about it. We've got non-polar. That's where the electrons are held perfectly. It's a pure covalent, perfectly in the center. Then we've got polar, which is where the electrons are held more closely to one atom than the other in the bond. And then the extreme is ionic bonding, where there is such a big difference in electronegativity that we've got the complete transfer. Those electrons move completely over to one atom and they're completely lost from the other. Okay, now that is something that we've really built on from GCSE, for example. That might be new knowledge to you, so it's really important we've got a strong understanding of this. You can still use your rules of metal and non-metal is ionic bonding, and non-metal and non-metal is a covalent. They're not incorrect. It's just we've added some more information. And there's a visual representation of what we mean. So we've got non-polar with Cl2, for example. HF is a polar covalent bond, and ionic bond would be a metal and non-metal, such as sodium and chlorine. In terms of the electron density, because this is a pure covalent, there is no charge anywhere. The electrons are held completely in the middle and the electrons are distributed evenly. Polar, you can see we've got greater electron density around the hydrogen, hence we've got this delta negative charge. It is not enough to give it a formal full negative charge. It is a delta negative. But with ionic bonding, we've got that complete transfer of electrons. We've got that full formal negative charge in terms of the electron density. So we've looked at polar bonds. So we're looking at the actual covalent bonds, or the ionic bonds, the intramolecular. Now we are looking at the molecule as a whole. We can actually say whether the whole molecule is polar or not just the bonds. So a molecule, for example, a molecule of water, contains polar bonds. Of course, we talked about that. H and O, they've got different electronegativities. Oxygen is more electronegative, so that's a polar bond and that's a polar bond. So we've got two polar bonds. And therefore, the molecule is going to have overall polarity, okay? But we can also have non-polar molecules. These CH, 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 and CH, they're all non-polar. So overall, we have no polarity on methane. But we do have some polarity in terms of the bonds of my carbon dioxide, don't we? Because my oxygen is more electronegative than my carbon, significantly enough that it does have a permanent dipole on these two bonds. But because this is a symmetrical structure, the polarity cancels out. Okay, so the polar bonds, they cancel each other out because they are symmetrical. So we end up with overall no polarity on a molecule like carbon dioxide on a linear shaped molecule. Whereas with water, there is an overall polarity. And it's because although we have got symmetry along this plane, that's fine, we don't have it along this plane here. So if I look at this molecule at this angle, on the top half here, we've got a delta negative overall. And on the bottom half here, we've got an overall delta positive because we've got the hydrogens on the lower part. So there is a polarity. If another molecule comes along and interacts with the top side of the water molecule, it's going to be interacting with the partial negative charge, the delta negative, and that's going to make it behave differently than if it approaches underneath the water molecule and starts coming across the hydrogens first because they're delta positive. So think about it like that. If another molecule, whatever that molecule is, comes across the top, it's going to have a different experience to if it approaches at the bottom. So overall, water we consider a polar molecule. So we consider water as non-symmetrical. Although it's got that one plane of symmetry, it has not got a full plane. The other plane that I showed you before, it is not symmetrical, okay? So water's got polar bonds and is a polar molecule. Methane has got non-polar bonds, because although we've got two different atoms, carbon and hydrogen are very similar in terms of their numbers on the Paulin scale. So they are considered non-polar. So overall, we've got a non-polar bond. And carbon dioxide, like I said, we have got polar bonds between the O and the C, but we've got that full symmetry on all planes, so they're going to cancel out. So no permanent dipole. So we're going to say that in terms of the molecule, water is polar, methane is non-polar, and carbon dioxide is non-polar. You'll find that molecules with a linear shape like carbon dioxide tend to be non-polar because of all the lines of symmetry they have, it cancels out the dipoles, any dipoles that do exist. Molecules that have got an OH, a nitrogen, or a hydrogen are usually polar. So for example, if I had methanol, and let's actually draw the full displayed. So really I should have that hydrogen coming off there. I'm going to have quite a big difference in polarity between the carbon and the oxygen here, this bond here. So this molecule is asymmetrical because if I draw a line here, overall we've got a delta negative charge on this side and overall we've got a delta positive / neutral on that side. So it is considered a polar molecule. And molecules which contain carbon often, but are not always, non-polar. So methane, for example. But like I said, if it's got an oxygen, a nitrogen, or hydrogen attached to it, then that changes the story quite a lot. And diatomic elements containing two of the same atom type are going to be non-polar, like with the chlorine that we were looking at.